So my next guest today is Zain Abadin. He's the Senior Director of Device Handling for Advantest. Welcome, Zain. Nice to see you.
Thank you. Thank you for having us.
Okay. So we're here to talk today about some of the challenges coming through with some of these new devices and applications, notably things like HBM, etc., for these large data centers for AI and also for the automotive world as well. You've come out with some new technologies to be able to handle some of the massive thermal excursions and power excursions with these devices. Can you tell us a bit about what's happening?
Yeah, so when it comes to HPC AI devices, what we found that the test requirements have undergone a step function increase. Yeah. So let's today talk about a couple of them. Thermal management is one of them. It's a big issue at this time, and also the requirement of 0 DPM, so defective parts per million.
Yes.
So in terms of thermal management, think of it as in final test, it used to be 50 watts, 100 watts, 200 watts. Mm-hmm. Now we are already testing 500, 1,000 watts, and the solution already out there for 2,000. And there is a talk of 3,000 watts. So that's what I mean. There is a step function increase in the test requirement.
Yes, that's a massive increase.
That's massive increase. Yeah. And then in terms of application of these devices, for example, AI device. So the requirement is 0 defects per million. It used to be 10 and 1 was a big deal. Mm-hmm. It makes sense. Because we don't want to have a defective chip in autonomous car. Right. We don't want.
No, of course.
So that's where the 0 DPM comes in.
Okay. Okay, so what's the solution?
So in this case, Advantest is proposing that we push the fault detection up the supply chain in the test ecosystem. What it means that in a test flow, you have wafer sort, then you have a dicing, then you have a singulated dies assembled onto the interposer, packaging for final tests and SLT. Mm-hmm. So in this, our proposal, after dicing, but before assembling onto the interposer, we propose to perform at speed final test-like testing on a singulated die.
Wow.
So this will eliminate the bad dies going into the next stage. So only good die will pass on to the next process.
Mm-hmm. Well, that's taking you into a whole new different world, because you're moving up into the front end of the process very much, and where the accuracy, the economies of scale, everything has to be so much tighter.
It does. And then another challenge is the packaging of choice for these packages. Our 2.5D 3D packaging is the packaging of choice. It's like Lego building, building with Legos, mix and match different components to get to the final product.
So how do you get access to that?
But in here now, the 2.5D and 3D package, there are multiple suppliers with multiple devices, with different materials, different coefficient of expansion. So if one chip fails in the package, the entire package is wasted. And that's a huge challenge to yield. Yield loss is a big issue in this situation, and it increases your cost, and also it does have environmental impact, because you are throwing away perfectly good dies just because of one single bad die.
One bad die.
So our proposal in this case is to perform singulated die testing after dicing, but before assembling onto the interposer.
So that way
this is true for logic. Yeah, it's true for logic as well as for memory. Right. Remember, nowadays the AI device, let's say, has a AI engine, and then it's surrounded by HBM towers. Mm-hmm. So what we are proposing is across the board, both for logic, let's say GPU or I/O drive or whichever device, and also for memory.
Right. Yeah. So basically, you're only passing over known good die, basically.
Only known good die that has been tested at speed at a die level. That's the big differentiation.
How do you deal with the massive thermal excursions when you're doing this?
Right. So it's the device that drives the solution. So in this case, when we say at-speed testing at a die level, it means we need to have a cooling capacity available at that point to control this thermal excursion.
Right.
So Advantest deploys active thermal control technologies, ATC technologies, across the board.
How does that work?
From SLT, FT, even in singulated. So these are characterized by high delta T and low thermal mass for fast response to modulate the chuck and maintain the dot temperature within certain guard band. And we also have feedback that we use from either from the chuck, sensor on the chuck, or sensor on the device.
Right.
And we complement it with the feed-forward methodology, like predictive cooling. So that's how we are able to.
Basically, you're monitoring it all the time and applying the
all the time and modulating the temperature of the chuck to control the temperature of the device.
Wow. It sounds like a massive feat of engineering.
In this case, we engage early, and like you mentioned, we are moving up the chain.
Yes.
So even during the device design, we engage early. We understand what the device is, where the high power generating components going to be in the package. So we do thermal simulation, we do TTV testing, we do live device testing when it's packaged in a lab setup. And so we are able to give the feedback and be ready. So all of it is done way before production of these devices start.
It sounds a great idea, Zain. I mean, you're introducing a new process step into the process. What has been the reaction of the industry to it? I mean, are they embracing it?
Yes, it is being embraced. They have to have this to get to the zero DPPM or to able to maintain certain yield level. You have to be able to test all these dies before they get onto the interposer or 2.5D or other packages.
I would imagine it must be quite a cost saving as well, with by not packaging all the bad dies, as it were.
Oh, there have been a lot of analysis. Of course, I mean there's billions of dollars at stake. So the idea is if you move an RMA or fault from let's say SLT to final test, to singulated test, or even in the wafer stage, it saves you tons of money. Even though you are testing more, there are more failures at the early stage, but then you're saving all the good dies that
so
go thrown
the earlier
away.
you catch the defect in the process, the more money you save.
Exactly.
Exactly. Well, very interesting. And you've got these systems currently rolled out, some of them in the field?
Yes, we are working with our customers on all of this. And beside this, as I mentioned, there are multiple insertions in the back end, right? So there's a wafer sort, then there is a wafer sort 2, then there is a final test, there's SLT, burn-in. So Advantest also we call it ACS, basically Advantest Cloud Solutions. We have a real-time data infrastructure that, because each of these insertions generating a lot of data. So we want to analyze and provide real-time action items. So when you are testing, you know what action to take. Is there any issue with the probe pins that is causing failure, or the failure that fault showed up in final test or SLT, can it be detected at the wafer or singulated die level, so that all the packages that go wasted that can be saved?
Yeah. Well, it sounds an amazing feat of engineering. I want to congratulations on it, and I want to thank you for coming in and telling us about it today.
Thank you very much.